All right. Homework should be out, coming around. Give your mark. Make sure your name's on top. Second page, right there. You go.
No, this isn't the worksheet.
That's like the
There we go. So you don't have do you need a packet?
I'll find
You
it.
sure? I got
I'll
extra.
find it.
I got
I'll find
extras.
it. I'll find it.
cleaned it this morning.
It's so awkward, right?
Awkward. Wow, guys, stop being so awkward.
How about 10?
This class is very
I don't know whose it is. It was just up there.
Yeah.
Okay, will you flip the lights down first, please? Thank you, my friend. Okay, so we are on that second page, pages 3 and 4. And I guess let's just start with number 1. Let's walk through these, see how we feel. Okay? This is a little different thinking than what we're used to, right? So it says, and please know this is probably all made up data. There's nothing to say that this came from a reliable source, and that's okay. So it says a story of an introductory statistics class in the fall asked students whether they ate breakfast the morning of the survey, and the results are as follows. So you have boys and girls, or gender, male or female, and if they ate breakfast or not. Everyone agree? So I have male, female. Yes, no. And then I have 66 and 125, and then there's a total of 191 for those people. 66 and 74, 140 of them. Then over here, this is 132 people, 199 people, and then they tell us that. So basically, how that 331 comes, if I add 191 and 140 together, I get 331. If I add 132 and 199 together, I get 331 as well. So when we do these, the easiest way to think about it is if you had everyone together and some of it, and then some of the problems, we're going to actually split the people. Okay? And when we split them in this case, it would be like, okay, all the guys leave the classroom and keep the girls. Maybe all the boys come back in the classroom, all the girls go out. Or if you ate breakfast, stay here. If you didn't, go out in the hall, and vice versa. So that's kind of how we have to think about what we'll be doing with this problem. And when we pick things at random isn't me going like this. That's not random. Okay? Random means that you somehow had some sort of device or mechanism that allowed you to pick a person out without subjecting you to any visual interpretation. So if we were to talk about these 331 people, what we could do is we could give everyone some sort of number, and then put all the numbers on a piece of paper, mix them up, put them in a hat. Put them in a hat or put them in a bucket so you can't see it. You're just reaching in and pulling them out. Okay? So that's kind of how you have to look at statistics. A lot of people will think, oh yeah, I randomly picked a number. Most of the time when someone says, hey, pick a number between 1 and 10, studies do show that most people pick 7. Why? I don't know. It's just that's the number. Now, I know you might be thinking and going, no, I was thinking 3. I know, but there's there's 7 billion people on the planet. They claim that this is what people are most likely to pick. If you're to pick a number between 1 and 10, you know me. Well, yeah,
I
that's true.
always pick 7.
But if, when people say pick a number between 1 and 10, I always say 5.12677322138.
4 or 7.
384. And people like do the pickle decimal.
9 will trip people up though.
Good. All right. So letter A, and I'm going to try and use some of the terminology. What is the probability that we have everyone in the room and we pick somebody at random, they happen to be female? So first off, let's figure out our denominator. What is the total number of people in this group?
Like 28 or something. 331.
Yeah, in this survey, not in this class, in the survey.
This class there are 14.
All right, good. Now, how many in this particular survey happen to be female?
199.
Female, 199, yeah, right here. So, if you had all 331 of these participants all together, what is the probability that someone was selected at some random number generator was picked? You have 199 out of 331 chance that you pick that person. Now, notice I haven't changed it to a percent or anything like that, have I? Nope. If I wanted to change it to a percent, I can go 199 divided by 331. It's going to give me some decimal. Then I multiply that decimal by 100, and it's going to give me a percent. But I can just leave it as a fraction just like that and say, done. Okay? So then let's go to letter B. Letter B. It says, what is the probability that a randomly selected student ate breakfast? So probability of breakfast. Okay, so again, all the students are participating, so you have 331 people. How many of those people ate breakfast? Yeah, you got 191. So you have a 191 out of 331 chance of pulling. So let me ask you this. Do you have a better chance of pulling a person who's a female or a better chance of pulling somebody who ate breakfast? Female. There's 8 more outcomes that could take place because you have 199 versus 191. Letter C. Letter C. What is the probability that a randomly selected student was male or ate breakfast? So probability of male or breakfast. Okay, now, this is where we have to be a little cautious. We're still talking about everybody in our study, so we have 331. So, are there males that ate breakfast?
Yes.
Yes. So, if I were to do this, if I were to say, the thing is I have 132 males. And of that 132 males, 66 of them ate breakfast, agreed? But then ate breakfast is also 191, so I don't want to go 132 plus 191. I want to also include the females here. So I'm not including that 66 because that 66 is already incorporated here. Does that make sense how I just said that? So we want a probability of males, 132. There's 132 males. There happen to be 66 of those guys had eaten breakfast. But I don't want to count them twice, so now I have to incorporate the females who ate breakfast in this study. And if we add those two together on top, I'm going to get 257 out of 331. So that's pretty likely that you had everyone all together and you walked up and found somebody and said, hey, are you a guy? Uh-huh. Hey, did you eat breakfast? Uh-huh. One of those outcomes, one or the other. There's 257 out of 331 of those outcomes that could take place. That's pretty likely. Let's see, letter D. Now this is where it starts getting a little, you have to, really use your reading skills to figure this out. D says, what is the probability that a randomly selected female ate breakfast? Okay, what is the probability that a female ate breakfast? Okay? What I did in this case is I said, okay, all the males step out of the room. So in the room, I just have the females. So how many people are in the room now if there's only females in their study? 199, good. So my denominator changed. Why is it not 331 anymore? Because I told all the males, see you later. Okay. And then, how many of those females happen to have eaten breakfast? How many females ate breakfast? 125 ate breakfast. So that's pretty likely. So if you start eliminating a portion of the group for whatever characteristics, you are changing your denominator. Then that's letter D. Letter E. Letter E. What is the probability that a randomly selected female, or what is the probability that a randomly selected female is, or a student is female, given the student ate breakfast? Okay, so now what I've done in this case is I said, okay, all you guys that walked outside, come on back inside. Oh, okay, so everyone comes in here, so now we have 331 people in the room. So now I'm going to say, if you didn't eat breakfast, go ahead and leave for a few minutes. So how many people, so we're looking at this. We're looking at what is the probability that a randomly selected female, given they ate breakfast. Okay, so how many people ate breakfast in our study? 191. Okay, so we just have the breakfast people together. How many of those breakfast people happen to be female? 25. And then letter F. Let's see if we can squeeze this down here a little bit. Letter F. What is the probability that a randomly selected student ate breakfast and is female? Okay, so now we're talking still all my 331. Everyone's in the room. So what's the probability of breakfast and female? So breakfast and female means you're talking about a female, and you're talking about the females that ate breakfast. How many females ate breakfast? 125. 125 out of 331. Okay? And that's really how you do it. Yeah.
So, you know when to separate the woman and the men when it says, like, out of the woman in the thing? I didn't read that.
If it says that given that the student ate breakfast, that means we're only worried about the breakfast people. Now we're figuring out male, females from that. Or randomly selected female ate breakfast. So then we're looking just for the people who ate breakfast and females and things like that. So it's a matter of there are no numbers up here. Everything that's in the grid are your numbers. There's no more numbers that you're going to have to make up. Okay, they're all given. It's just a matter of making your ratio work out. Can we move to number 2? Yeah. Cool. Says a group of several executives were asked what kind of cell phone they use. Okay. Again, is this made up data? Sure. But we're just trying to get the facts about this. Let's see right here. So we have males and females again. And the iPhone. You got the Samsung. You got the Google. And then you got the other. Other might be called a flip phone, right? Ah. 8. Okay, so we are missing totals of each row so far. So I'm gonna add up this row right here to get a total over here. All right, let's see. That's 6, 10, 2, 6, 13, 14, 15, 250. Is that right? So I'll also just add it just straight across, right? 50, 50. That looks like 200 people here, I believe. 50 and 50 is 100. 92 and 8 is 100, 100, 100. And then I also have my totals down here.
441.
Whoa. Okay. 6, and then you got 1, 216. All right. And then this one I have 126, 90, 18. And then my total of people is 450. So that should equal 450, and if I add across that way, should equal 450. We good? Everyone feel comfortable how I generated those numbers? So what is the probability that a randomly selected executive was a male? So letter A, probability of a male. Probability of a male. So we're talking about everybody all together. So you have 450 people in this room. Must be a pretty big room, I imagine. How many males are you talking about? 250. Now some people would say, hey, should we reduce the fraction? I guess you should, but I'm looking to see that you can figure out the probability. I'm not testing you if you can reduce fractions. That's a skill you should have.
That's easy stuff.
Well, for some might think it's a tougher activity, but we'll figure it out. What is the probability that a randomly selected executive uses an iPhone? So probability of an iPhone. Okay, so we still have everybody in the same big room. How many iPhone people are there?
216.
216.
Out of 450.
Yeah. What is the probability that a randomly selected male used an iPhone? Or C, the probability that a male uses an iPhone. Okay? So what we did in this case is we said, all females, go. All males are back in the room. So how many males are in the room in our study? 250. How many of those people that are males use an iPhone?
124.
There you go. So that's almost half. Let's see, letter D. Letter D says, what is the probability that a randomly selected Samsung user was a female? So we bring everybody back into the room. Said, okay, everyone who has a Samsung, stay here. Everyone else, go outside. So how many? So I want the probability that it's a Samsung is female. So how many people have the Samsung phone? 126. How many of those people happen to be female? 50. Okay? And then letter E. What is the probability that a randomly selected executive was male who what is the probability a random selected executive was male and uses the iPhone? So everyone's in the room. We have the probability of male and Samsung. Okay? So we have everybody that's in the room. So we have 450 in the room. How many males use the Samsung? That's it. That's it. That's all you got. All right. Make sure your names are on those and pass those forward, please. Just that second, page 3, 4. So you have to separate my name. But don't worry. Don't worry. I have a. If you wanted it all together still. Dang, I can't give these away. sir.
Thanks, homie.
What are you saying?
I just want page 3 now.
You legit speak so low.
I already put it in 1 and 2.
Speak high.
And so if you had finished, because I didn't really get it until
Oh, almost there. We're
Almost.
gonna get it one day, stir up.
One day we will have perfection.
Okay, so what do you want to say?
What did I do? All right, my friends. Let's take a look at these notes. So one thing that we're walking with statistics is how do we organize it? How do we organize it to look at it? And there's some ways we can organize statistics to look at it, and it actually visually makes sense. So we're going to go through a couple of things. All right, so we have disjoint events and we have conditional probability. I think those both showed up on your page. It says disjoint events that are two events that cannot happen at the same time. So that would be like if I had a deck of cards. Still with me in this conversation? Actually, let's go even simpler. I have that singleton die. So I have 1, 2, 3, 4, 5, 6 on the die, correct? So what's the probability that I take my die and I roll it once and I get a 1 and a 2? Yeah, it's not going to happen, right? So both events. So that would be like two disjoint events. So they can't happen at the same time. That'd be probably a simple way to think about it. And then conditional probability is the probability of one event happening given another event has already happened. Okay, so that's kind of where we've actually said, okay, what's the probability that this person has an iPhone being it's a female? That means that we told everyone to leave. That's a male, and then you deal with the females. Okay, so there's some sort of prescription you're putting with your information. Okay, again, this is made up fictitious data, but we'll utilize it to what we have. So there's a survey of 350 CCHS students has been taken to see if they've started studying for finals yet. Well, hopefully they haven't started studying for them yet. We just started the semester, but let's just pretend we're 3 weeks ago. The results of the graph are on a segmented bar graph. We have a bar graph that are broken into yes or no's. Okay. These numbers down here represent 9th, 10th, 11th, 12th grade. These numbers here represent the number of 9th graders, number of 10th graders, 11th graders. So you have to add the two together. All right, so let's see if we can answer these questions. How many students surveyed were 9th graders? How much? 85. Yeah, 85. Yeah. So there's 85 because I just add those two together. How many students have already started studying for finals? Excuse me. So I'm going to go 50, 35, 35. That's 70. That's 120, 120, and that is 150. Oh, thank you. Thank you. Blue is right. Yes, studying. Let's see. 35, 60. That's 95. 200. So 200 kids. If I add the 40, the 65, the 60, and the 35 together, I get 200. Is that all right so far? Okay, now we're going to start selecting different ways. If I were to select a random student, what is the probability that I pick a 10th grader who has not started studying? Okay, so how many 10th graders had not started studying according to this data? 35. Okay, so I have 35. But then I'm talking about my whole group. How many people were in my group? 350? Is that what it was? Yes, good job. And I guess you could reduce that to give you 1 out of 10. And then if I were to select a random student, what is the probability that I pick a 12th grader? So how many 12th graders are listed up there? 70, and that's still out of the 350. And I guess you could then reduce that to get 1/5, but again, I'm checking to see if you can do statistics, not reduce fractions. Letter E says, if I were to select a random student, what is the probability that I pick someone who is in either 10th or 11th grade? So everyone's still together, so there's 350 people. And how many 10th graders were surveyed? It's like 95. And how many juniors? That's 100. So my denominator will be, or my numerator will be 195. So if I had everyone together, what's the chance that I draw a 10th or 11th grader? 195 out of 350. And then if I were to select a 12th grader, what is the probability that I'd pick someone who has not started? If I were to select a random 12th grader, what is the chance that I pick someone who has not started studying? So I'm only looking for the 12th graders. How many 12th graders are there? 70. And how many did not start studying yet? So 30 out of 70. And again, you could reduce that, but again, we just leave it like that. And then if I were to select a random student that has been studying, what is the probability that they are a senior? Okay, so how many seniors studied? 40? So 40. And then how many people studied all together? Well, didn't we add those up already? 200? And again, I could probably reduce that to 1/5 would be fine. Not too bad, is it? May I move on? Yes. Yep.
C, vamos aqui.
Huh?
I said C, vamos aqui. Which is, yes, come here.
Yes, come here.
Not move on.
Wait till
All right, a tree diagram is a visual representation of data, and you show outcomes versus on their branches. And as the branches continue to go further and further out, you multiply those fractions together to find their probabilities. Okay, this is where we need to think of conditional probabilities, the probability that an event happens after another event has happened. Okay, and I think we can make more sense of this in a moment. You guys have all this on there, right? All right. So, this is already a tree diagram set up, but let's read the example first. It says a local car dealer is interested in what vehicles are popular. Okay, that makes sense. If you're selling cars, you want to have the popular cars, right? A data analyst at the dealership surveyed 100 people and found out their age category: young, which was less than 25 years old, or old, which was older than 25. Okay. Man, these guys above 25, dude, he's old.
nice groups.
Yep. What kind of car they prefer or SUV? The results right below are in the diagram. Okay. So it looks like of the 100 people surveyed, 35 young people and 65 old people. Is that okay? So technically, if I were to get to this branch, it's a 35 out of 100 chance. If I get to this branch, it's what? Yeah, 65 out of 100. Now, in order for these branches to work appropriately, if I were to add 65 over 100 and 35 over 100, I get 100 over 100, which is the same as what number? 1. Okay? So each of these branches always have to be able to do that. Okay? Now, we're going to go to this branch, but I have to incorporate this eventually. So how many people are we talking about right here between these two? 35. So you have a 26 out of 35 here. And you have a 9 out of 35 here. I'm going to pause that for a moment because we'll actually come back to it. And then here, we're talking about 65 people. So this is a 40 out of 65. And And this is a 25 out of 65. Again, put those in parentheses. Now, what did I say the branches have to add up to? 100%. So if I were to go 35 over 100 plus 65 over 100, I get 100 over 100. 100 over 100 is 1. Okay? But right now, those far right values, 26 out of 35, 9 out of 35, 45 out of 65, 25 out of 65, that does not add up to be 100% or 1. So what I have to do is I have to go along the branch and I have to multiply. I was going to grab a calculator to do it. I have a sneeze that wants to come. It's coming.
Look into the light, look into the light.
Watermelon.
Me
No,
too.
it's
Dude.
God.
I hate when that.
Alright, so follow my branches. We're going to do this with a highlighter. Okay, I'm going to go this branch to that branch. Okay? So I'm going to multiply 35 over 100 times 26 over 35. And if I do that math correctly, it's going to give me this branch here is 13 over 50. So what is the probability of these 100 people that I were to select somebody who is young and also wants to buy a car? 13 out of 50. Okay, it probably was 26 out of 100 originally. And then I'm going to go along this path here. Another highlighter, different color. So I'm going to still go along with these guys, but now I'm going to go down this branch. Okay, and if I do that, I'm going to go 35 out of 100 times 9 out of 35. So I get 9 out of 100. Stop. Okay. Okay. And then now we're going to go this branch. So what two fractions am I going to multiply together here? So that actually gave me 2 out of 5. So what's the probability I select somebody who is old that wants a car? 2 in 5 chance. And then my last path is this one. Right there. So I'm going to multiply 65 over 100. Times 25 over 65. So I get 0.25, which is 1 in 4. So what did I say these have to add up to? They have to add up to 1. So if you used a calculator, you go 13 divided by 50 plus 9 divided by 100 plus 2 divided by 5 plus 1 divided by 4. I add it all up. This one, this one, this one, this one added up, sum up to 1. It means my tree diagram is correct. So that would be now you're just literally looking. Okay, what's the probability I pick somebody who's young who wants an SUV? 9 out of 100. What's the probability I pick someone who's old who wants an SUV? 1 out of 4. What's the probability I pick somebody who is young and they want a car? 13 out of 50. What's the probability I pick somebody who is old and wants a car? 2 out of 5. Okay? So the tree diagram, I think you might be able to see that it's a pretty good visual representation of events. And these aren't disjoint events. This isn't, what's the probability the person is old and young? They're either one or the other. It's not and. So they said old on there is older than 25. That's ancient. Got some old people there.
Well, King Tut died at 18.
That's true. All right, where are we at? We should be good. All right, you need to get a ride to school, you need to get a ride to soccer practice. Your mom drives you 80% of the time. When your mom drives, the probability to get there on time is 95%. If your dad drives, the probability of getting you to practice on time is 65%.
Sounds like you know this,
Huh? Yeah, well,
No,
you know.
that's so accurate. though.
Unless your dad's
2
the
miles
coach.
an hour.
All right, ready? So here's your mom. So your mom happens to drive 80% of the time. And I'm going to make 80% 0.8. Is that okay? So I'm not going to worry about fraction. That means dad takes you 20% of the time, right? And 20% as a decimal is 0.2. So is 0.8 plus 0.2 1.0?
Yes.
Cool. Our branches are working so far. Then it says that when your mom drives you, your probability to get there on time is 95%. So on time is 95%, so we're going to say it's 0.95. So late would be how much if mom drives? 0.5, right? Or point. So 5% of the time. Cool. And then dad, get there on time. I think dad's stopping off at the Home Depot or something. And then late. 3.5. Yeah. Now you remember I said that this branch has to add up to 1, right? Well, if I go 0.95 and 0.05, I get to 1 already. So now that's not going to work. So I need to multiply each branch. Okay? So I'm going to go 0.8 times 0.95. That gives me 0.76, which is 76%. Agreed? And then I have 0.8 times 0.05, which is 0.04, which is 4%, right? And then I have 0.2 times 0.65, so that's 13% of the time. And then 0.2 times 0.35 is 0.07, which is 7% of the time. So if I add these together, that's 0.8 plus 0.2, 1.0. It works. You're ready to go. What is the probability that your dad drives you? 20% of the time. Right? What is the probability that today your dad drives you and you get there on time? Well, dad drives you and you get there on time?
65% of the time.
No. 13%. It's the far branch. Okay, or the far leaf, I guess you could call it if you wanted to. What is the probability your mom drives you and you get there late today?
4%.
4% of the time. Good. 0.04. And what is the probability that you get there on time today? So do you know if mom or dad drove you? No. But what's the chance you got there on time? 0.76 plus 0.13. 0.89. 89%. Hey, what's the chance you get to practice on time today? 89%, coach. Okay. Doesn't seem like horrible math, but maybe you guys are just like being awesome and doing it. Okay. And the last thing we're going to talk about is something called the Venn diagram. And things we have to look at here is this is event A, this is event B, and this is event A and event B happening. Okay? So the probability a student belongs to a club is 0.4. So club, so 0.4, which is 40%. Do you agree with that? Yeah. Okay? the probability a student works part-time is 0.5, which is 50%. Agree? The probability that a student belongs to a club and works part-time is 0.05. So this is both events. So that's 5% because 0.05. What is the probability that the student belongs to a club or works part-time? Now, one thing we have to incorporate here. 40% of the kids are involved with the club, but 5% of them are these kids. So this is actually a 35% is just in the club. This 50 is actually 45% because we still have that 5% there. So what is the probability that they belong to a club and, or they work? Talking about 80% of the students. Okay? I think you guys know which page is your homework, right?
4 and 5.
Is it 4 and 5? Is that what it is? 5 and 6. Page 5 and 6. Keep up the good work, guys and girls.